Okay, we're going to start talking about projectile motion. So I want you to imagine a cliff, and we're going to have somebody run off the cliff. Okay, they're just going to take off running, and they're going to run off the edge of the cliff, and they're going to go in a motion like that. What I want you to realize is outside of air resistance, there's nothing to slow them down in the east and west direction. So their velocity at this point, if we were going to look at their velocity at that point, and I'm going to draw that point right here, they would have a velocity in this direction, and they really don't have any velocity in the downward direction. As they leave the cliff, as here for example, they still have the velocity in that direction, and they're starting to gain velocity. And as we draw these dots, the velocity in the horizontal direction is staying the same, and the velocity in the vertical direction is growing. So what happens is the velocity horizontal, VH, is constant. Okay? And since it's constant, the distance horizontal is simply equal to the velocity horizontal times time. In other words, if we look at the distance in the horizontal direction of this incident here, this distance from the bottom of the cliff to out here follows this equation. Now, the vertical velocity operates under g. And right when the object is here, it has no vertical velocity. So VI is 0. And then it does one of these, and down here, the velocity vertical final equals VI plus GT. This should look very familiar. This being 0, it's gone. So VVF equals GT. So when we look at a problem like this, we're going to say that we have a 100-meter cliff and an object going straight off the cliff and coming to the ground. And the object has a velocity of 10 meters per second. Now that's obviously in the horizontal direction. What determines how long this thing's going to be in the air is right here. Doesn't depend how fast it's going off the cliff. If it's going real slow off the cliff, it'll just land down here somewhere. If it's going real fast over the cliff, it might land out here somewhere. But the amount of time that it takes doesn't matter. It's only dependent on the vertical distance. So, how do we get this time? Well, we know at this point right here, up here, we know that VVI, velocity vertical initial, is 0. So we know that distance vertical equals VVI plus 1/2 GT squared. We know this is 0. So distance vertical equals 1/2 GT squared. We know the distance vertical is 100. So if we were to rearrange this, 2dV over g, square root of that equals time. we would have our time. So we're going to do that real quick. Let me find a calculator on this computer. It won't let me do it. Okay, I'm going to do it off the screen because it's recording right now, so it won't let me do it. I have a calculator on my phone that I'm going to use. Okay. Oop, that's the wrong thing. So 200 divided by 9.8, okay, square root of that, I hate phone calculators. Let me see if I can get this one to behave itself. I think I have to get rid of that. And you can see the writing is all over this thing. Calculator. There it is. Okay, so I come over here and it's 200 divided by 9.8 equals that, and the square root of that is right here, 4.5. So I come back and my time is 4.5 seconds. So if it's going to be in the air 4.5 seconds, but how far is it moving horizontally in this direction? Well, we know that the velocity horizontal is 10 because that's what it went off the cliff with. So distance horizontal equals velocity horizontal times time, and 10 times 4.5 is 45 meters. So this is going to be 45 meters from the cliff. All right, that's for the ones running off a cliff. Now, there are also ones that run like this. Here's the ground, and it goes up and it goes down. All right, at this point up here, VVI equals 0. The time that it takes to go up equals the time that it takes to go down. So what we want to do is, if we know how long it's in the air, or we know distance, or we know whatever, we also know that these two distances right here, the time it spends going up and the time it spends coming down, are equal. So what we tend to do is, a problem would sound like, you know, you've got something launched at a certain angle, and it's in the air for 10 seconds. Let's say something is in the air for 10 seconds. Okay, time is 10 seconds. That means it spent 5 seconds going up and 5 seconds coming down. Okay, we're going in this direction. So we could calculate VVF right now. Okay, because VVF equals VVI plus GT. Same equations we used before. 0 plus 9.8 times 5. Okay, and that is what? 49.2, something like that, meters per second. Well, if something started at 0, okay, and now it's going 49.2, we know that it left the ground with the same speed that it hit the ground with. We could calculate all kinds of things. Distance equals 1/2 gt squared. We calculate that. We could calculate distance horizontal equals velocity horizontal times time. And that would be the whole time, 5 plus 5. Okay, but here's the thing. I know vertical velocity, but I don't know horizontal velocity. Let's just talk about that for a second. When an object leaves the ground, it has a vertical velocity and a horizontal velocity. Okay? Its actual velocity is somewhere in there. So let's say that I launch something with a 30-degree angle and a speed of, this is 30, and a speed of 10. Well, what does this mean? Well, it's going to go up and down. But if we look at the vertical and horizontal velocities, this is the velocity that that's 10, right? Here's the velocity horizontal. This is a 30-degree angle. And this, because of the vector components here, I can move it over here, and this is velocity vertical. And we can use SOHCAHTOA to do some solving. So this is just an introduction. What I want you to do, I'm going to put the assignment on as well for Monday. I'm going to have you read the chapter for one thing, and then I'm going to have you look at a few of the problems. And then we're going to come back through, and we're going to spend a lot of time on figuring this stuff out before we get too heavy into problems. So you have a good weekend, and we will see you Monday.